Hey folks, how's everyone doing? Okay, looks like the class strength keeps coming down. We might have to enforce attendance from next week just to make sure people come. Um, okay, so let's look at lecture 10. Um, this is, okay, yeah. So lecture 10, so mini project 2 will be released this Friday and due 2 weeks later, and we'll work in teams of 2. So maybe Arnav, we can have a way that they can put in their team names, team members, and have a spreadsheet for that. So we can form teams of 2. Yeah. Great. Thanks for calling that out. I think it should turn on in a bit. Okay. So any other logistics? Anything else from your end? Okay. So like we said last time, some of the upcoming topics. Is there an echo? Are you guys sensing an echo? Or is the sound okay? Sounds good. Okay. So some of the upcoming topics is chatbot and their design, prompt engineering techniques, pre-training and fine-tuning, a little bit on multi-model AI models, and quite a bit of time on agents and agentic AI. And if we do have time, we'll look into these things. But some of this, like LLM guardrailing, will already cover in the industry use cases here, because guardrailing and red teaming, so red teaming, guardrailing, all these are part of pushing a LLM system into production, is to make sure that there is AI safety enabled for production use cases. So typically it can take anywhere between a couple of weeks to a couple of months to clear the red teaming compliance, and it's not just like following some standards, but actually testing your model to see that it doesn't respond to malicious inputs or doesn't generate malicious responses, right? Either way. So there's a lot of tests that happen in typical red teaming efforts, especially if your model is very generative in nature. So we'll probably cover that more here. Okay. So last lecture we looked at training objectives for BERT. We looked at kind of a current trend. I see there's an echo from the Zoom. Yeah, so we looked at some current trends on agent systems that talk to each other and then come up with very interesting outputs, and that kind of brought up a little bit on AI safety as well. So today we'll look at a practical business use case. We finished with sentence BERT. I think we also covered sentence BERT here. So we look at a practical use case of sentence BERT with Instacart as an example. So we'll look at some Instacart. How many of us use Instacart here? Very few. Okay. Do people use something else or do you actually go to the store and purchase? How many of us are direct, go to store and purchase? Okay, so maybe it's only me. A little bit lazy. So that's good. Drive to the store, get what you want. So Instacart, if you use Instacart, then if you want to make bulk purchases, it's really helpful. So we'll look at how Instacart looks at search relevance and autocomplete, and how it uses the two-tower architecture to do this, right? We'll also look at a little bit on prompt engineering best practices, although this has been evolving over the last couple of years. So you had to do heavy prompt engineering before to make the LLM respond in a manner that's suitable. But now LLMs are much more responsive and performant, but you still need to do prompt engineering uh, to kind of maybe focus or guardrail the LLM, right? So it's more on that side, but you want to make sure that it's not responding to irrelevant queries. It's able to respond in a friendly way and things like that. You still need to do guardrailing and prompt engineering. So the prompt engineering has become more nuanced from what it was a couple of years back, where you really had to handhold the LLM, and you don't have to do that as much right now. But it's still kind of very useful to uh, do at least use some parts of prompt engineering and look at that uh, in some examples today. And then we'll go through paper presentations. Okay. How many people presenting today? 2. So that's one team. Was it other team? The team is, they're on, sorry.
There are 2 signed up for today.
2 sign up for today. Okay. Yeah, if it's a no-show, then there'll be, like we said, I mean, if we have to reschedule you and you haven't given us notice, and if it's upsetting the schedule, we might put in a 20% penalty. If you're like last minute, I want to reschedule, that's a little bit of a problem for us. So maybe Arnav, we can make a note of that. If it's a no-show, then you'll incur a penalty if you're rescheduling without notice. Okay. All right, so yeah, so we'll look at, so there's 2 articles I've referenced here. These are 2 blog posts from Instacart. Pretty interesting use cases for transformers, for business predictions, right? More than just generating responses, but actually using the 2-tower architecture and the encoding transformer architecture for something really interesting. So let's take a look at that. Yeah, so application of sentence transform embeddings to Instacart recommendations, right? So, so I think Instacart came up with a system called Items, which is Instacart Transformer Embedding Systems for embedding queries and products. So you have an encoder for the query, basically like a sentence BERT model, all of that. You go through the whole attention and feed forward and all of that. You get a token out of this, and you get an embedding out of this, and then you also get an embedding out of this. And then the standard cosine similarity. If it's very similar, the query is similar to the product. So recommend the product for this query. So people are searching on Instacart for some products, and you want to surface different products. So that's the idea here. So the 2-tower architecture is kind of self-explanatory. There are 2 towers. One represents the query tower and one represents the product or customer. In this case, it's product. The sentence BERT that we looked at earlier is a Siamese 2-tower, where the weights and the layers of the 2 towers are identical. So the weights are tied in training. So it's actually identical. Yeah, so they're tied together, and the gradients are computed keeping the tying in place. So now the weights are tied. But here with the Instacart recommendations 2-tower, the 2 towers don't refer to the same kind of object. So, but they refer to a product and a query. And there may be different things you want to encode for a product tower versus a query tower. And hence the 2 towers have distinct weights learned from data, right? So, and in the industry, people also use multiple towers, multi-tower, not just 2 towers. You can encode different kinds of data for your end application. If you have different kinds of signals and you want to have deep representations for those signals, then you can have multiple towers, and then they can pull together in the last layer, and you can then do a classification or something. So multi-tower architecture is also something that people look at. So here's an example of what we're looking at with this application. Is you type in a search query, let's say pecans, and then this is from an actual search, and I get different responses like this is, okay, this is not relevant, but it's sponsored. So it comes at the top. These are relevant. And this is also a byte again because I bought it before. And then these are other ones. There's like sorted by bestseller as well. And then there is the rest. So there is, it's not just that the results are relevant, but they're also sorted in a specific way. And somehow the sponsored product also shows up, not so relevant, but it shows up because, yeah, whatever. They need to show sponsored products too, because they get revenue for that. And yeah, I'm not sure. Oh, it has beacons though. Wait, yeah. So I was thinking, I think I got confused by this. When I see mesh tool, I like, that must be dates, right? But it's actually pecan, mesh tool, whatever, etc. I think it's some pecan chocolate delight. So there's pecan in that, but it's also something else. So it's not completely irrelevant. It's like relevant, somewhat relevant, less sponsored. Okay. Okay, so the question is, how do you go from this, which is the query here, and then to this? And then you may want to surface a top, like on my phone, if I look at Instacart, let me see how many I can see on one page. So I search for something like, okay, this is a different view. Oh yeah, I see six about, yeah. I can see about 6 on my phone. So this makes sense. So you basically want to not just recommend, but also rank and list the top 6, and then you can scroll and get the next 6 and so on and so forth, right? So one question that Instacart had to deal with is, like, I want to do a training of this sentence BERT architecture and get good query embeddings and product embeddings, but I need good training data. So what's my training data? For this query, this is a good search result. And for this query, this is not really relevant because that's a negative example. A good result would be relevant, and then not so good result is irrelevant, right? Or a negative example. So one of the things that they took as signal is not just like Instacart already has a search engine, right? At the time at which they were building this product. So there's already like search and retrieve results, and you can pick from there. But they didn't just look at search results, they looked at search results where people actually converted to a purchase. So it's not just relevant, it's very relevant because you actually searched and then customers actually converted. So like if you search for orange, you might actually see search results that have other things in here because of the way search works. There's a separate search engine. But then these are the ones that actually got converted, so termed as positive examples. And then the question was, how do you come up with negative examples? So if in my search results, there were products that converted, we treat them as positive examples. But if they did not convert, are they negative examples? No, right? For example, if there's ice cream and then there's something new in there's a new product that just came out, right? It probably didn't have any data or any conversion history so far. No one's purchased that, it's a new product. But it's still displayed in the search results. But then if you say that's a negative example, that would be bad data. Because I am just saying whatever I didn't convert in my search results could be used as negative data. So that doesn't work. So it's, in this particular example, it's easier to identify positive examples, and it's harder to identify negative examples unless you kind of are a little bit more careful in how you pick your negative examples. So, for example, if in Instacart you can pick a different any kind of a store, right? Let's say you pick Safeway, and then you search for ice cream. You see all of these are ice creams, and they're all relevant. So, and some of them might have converted, and some of them haven't converted so far. or some of them might have converted to a purchase but have very few purchases, or some of them have zero purchases and some of them have a lot of purchases. So you have these three different buckets. So I have to be careful on identifying which of them are negative examples. So that's where they came up with an interesting solution where they said, let's actually focus on what were positive. Like for example, for query 1, P1 converted, so that's a positive example. For query 2, P2 converted, so that's a positive example. So all the diagonals are positive examples, right? Now I can create a matrix by looking at all the other examples from the training data, right? And then I can call it an in-batch negative. So I'm creating a negative set from not the same pool of search for a query, look at the results, but look at different queries and look at their results. And now you form a matrix out of that and you have all pairs now. So for query 1, we didn't pick P2 in positive, but P2 is now available as being a candidate for negative. And P3 is a candidate for negative for Q1 as well, and so on. So all the off diagonals are candidates now for being negatives. And this is better than just looking at one search query and then saying whatever didn't convert is negative, right? Because now we're looking at different search queries and then mapping it out. You might still have some bad negatives here, but much fewer than the previous scenario, right? So this is what they call a vanilla in-batch negative labels. So you get a lot of negative labels for every positive label here, right? Because the number of diagonal entries is much fewer. Like if you have an n by n matrix, the number of diagonal elements is n, but the number of off diagonal elements is order n square. So you'll still have to do negative sampling, downsampling, to kind of make sure your classes are balanced between the positive and the negatives for training, right? So that's a vanilla implementation of the in-batch negative. But they also looked at something very interesting called reweighted self-adversarial negative. This is where they say, let's just train an initial model with a lot of negatives, and then let's look at the ones that it's finding it hard to predict as negative, and the ones which are easy for it to predict as negative. The ones that it's finding hard to predict as negative, let's give it a higher weight in the training. So you see those become darker red. Like these are somehow in the initial training, the model's not able to get it negative with a high confidence. So you want it to be more adversarial. So it's kind of a more adversarial example. So you want to weight it higher. So you force the model to actually predict it as negative. So if you force the model to learn representation, so you can predict it as negative, right? So here's a couple of examples for easy and hard negatives. Like if the search query is, let's say it's query and product, right? So if the search query is tortilla and the product is coffee mug, tortilla and coffee mug, they're not related, right? Not really. Maybe you have coffee with tortilla, but tortilla and coffee mug are not related. Okay, so that's straightforward. That's an easy negative. Let's look at a harder negative. So from tortilla, we go to what do you call this? Tostitos. Tostitos tortilla chips. So one is actually a tortilla. It's a bread, and the other is like chips. Both are a tortilla, but they're not the same. So if you want to be precise, then this is actually a negative example, but it's somewhat related. So that's why it's a hard negative. So if this was labeled negative and the model didn't get it negative with a high confidence, then in the reweighting, this particular example will get a higher negative weight. So the model's forced to learn how to predict this example as negative. That's like adversarial reweighting that they use to get this right. Does that make sense?
So we start with easy examples,
Yeah.
like we do with kids.
Yeah.
Then as they grow,
Right.
we give them harder and harder tasks.
And you use the predictions to understand which ones you're getting it right and which ones you're not, right?
You don't just throw a three-dimensional matrix model
Yeah, I think in statistics it's also called boosting. We're kind of doing boosting where you learn from what didn't work before and say, I need to do better on these examples. So I can learn more richer representations. I have better differentiation power for the model. The model is able to differentiate the nuances better than before.
How do they progress from easy to hard?
Yeah, so we'll look at an architecture on that. It's a good example. That's a good question. So this kind of, so this is one thing that they pay, like these are things, these are very interesting things when we say that, okay, I have a two-tower model, what do I do now? Train it. But the question is, where are the signals coming from? Where are the positives coming from? Where are the negatives coming from? These are industry specific. You have to look at your business use case and say, okay, I think these are the converted search results are positives. Like you have to come up with things like that. No one's going to tell you that this is how you need to label them as positives. You have to look at the data and say, yes, converted search results make sense. It's a good signal, right? So identifying signals for positive, negative in the data is an important part of using LLMs for business use cases in the industry, right? The other things that they also look at is, I'm just going to pause here because I think my charge is low. So the other thing they also look at, which is very instructive because they've considered different things, is expanding the product signals, saying that, hey, I search for something and I have results for that. Can I add something similar? For example, if you're looking at not just using product titles but also product descriptions, you'd say, well, instead of just organic milk, let's use organic 2% reduced fat milk because I get it from the description. So I can expand the queries and the product mappings by using product description to augment augment the signals as well. So this enables you to get more data, right? By just saying that, hey, don't just say, searching for milk gives me organic milk, but also it gives me organic 2% reduced fat milk. So you can add more data that way, so generate more data that way as well. And the other thing that they also say, look at is like products that just got launched or are new to the Instacart ecosystem, they also get surfaced through data augmentation. Like if you had some other brand of milk that's really new, you still know that it's in the category of milk. So if you had some mapping of a search query to a milk product, you could also map that search query to this new brand of milk that just got launched. Although it didn't have any conversion, because you're looking at converted search signals, you didn't have that for new products. But because of this category-based relationship, you can use category or even semantic search. You can just say, hey, this is how I'm going to actually add more data. So I can even cater to the new products and not just existing products. So these are two things that they also done as part of their training.
Question.
Yeah.
So this is for multi-tower, like the idea is to use two different data sets, queries, and results. Do you also include things like user embeddings to go with that to create a unified what the user is looking for?
Yeah, I think that's a good question. So here in this particular case, they're not looking at user information as such. So it's more like a better match between query and products overall. But I'm sure that they have a different model which they haven't spoken about. But typically you would do that. You would say if either I include it in the same model or I have a different model that says for this user, for the product results that you gave me, these seem more relevant based on their past purchases. So you could have another filter that actually takes these generic query product search relevance rankings and then filters it further for personalizing for user behavior. And actually, if you look at I'll look at this question too. So if you look at typical recommender system design, they are multi-stage. There's no single model. This is something I don't know if we have time for it, but let me just list it here. Let's say you had 100 million products that you can recommend for any given query. You'd have multiple stages of ranking and filtering, right? In the beginning, you might just say, let's just filter these 100 million products based on uh, maybe there's some keywords for the query, and these keywords match, these keywords don't match. Let's filter. It's just a rule-based filtering. You didn't use any model. Then you might use something like collaborative filtering, and then say, let's look at, for this particular user, which products are more useful, right? So then you include the user behavior in that, and then you reduce the search space. So maybe I'm from 100 million, I'm down to maybe like 1 million here, and then from 1 million, I'm down to like maybe 100K after collaborative filtering. And then I'd say, okay, now I'd use a two-tower architecture, because collaborative filtering is nice, but it's not that powerful of a recommender system. So I have an initial behavioral understanding of what the user will like, but I want to refine it even further. So then you can go towards a two-tower architecture. And then this might bring it down to 10K. Then you might have a ranking model and say rank these things and bring it down to top 100. Then you might have other things like diversification and other filters in place that brings it down to top 10 or top 20. So yeah, that's a good point you brought up, which also connects to this in that recommender systems are typically multi-stage. And because the search space is so huge, like I can't have a two-tower model search across 100 million products efficiently across hundreds of millions of users, or how many users that ecosystem has, right? It's simply not so efficient. So I'll have to kind of like use rule-based systems and simple models with low latency, and then have deep learning transformer models with a little bit higher latency towards the very end. So you're not so overall you're not incurring a whole lot of latency. Okay.
Another question.
Yeah.
I just checked. So if I put in organic milk, right, it will give me organic milk.
Uh-huh.
But if I put in non-organic milk or not organic milk, it still gives me organic milk. How? Any explanation why?
Yeah. So that's a good question. So there's probably like, we look at it, but all of it is semantic search. Does organic milk come up with the first, or the non-organic milk comes in at the top?
Seems only show me organic milk, even if I put non-organic milk.
Oh, even if you put non-organic milk,
Yeah.
it shows organic milk.
So it does not seem to understand what.
Yeah.
or
So
not.
there's a little bit problem with the embedding there.
But like say if I search for ice cream, no sugar, it will give me some ice cream with low or no sugar. So
It's working in some cases and not in the others.
any idea?
That's a good one. Let me search myself as well. Very interesting. Did you search for non-organic milk?
For non-organic milk.
Maybe the model never seen non-organic
Yeah.
products, so it doesn't know that the closest thing is organic.
Well, then we need to search for milk and see if you get organic milk too. Then your hypothesis will be right. So I'm searching for milk. Get a lot of organic. Yeah, maybe there's heavy bias towards organic milk. So the data itself, the number of products that you see, there might be heavy bias. Everyone's going organic. So like maybe the people who actually buy non-organic through Instacart. So Instacart has already extra fees, right? So you're willing to pay extra fees. So maybe you're able to afford organic milk more. So there might be a bias that.
But in terms of semantic understanding, it does not seem to understand the logic for the word, right?
Yes and no. I think it could be that there is a semantic issue. It could also be a data bias. Like if all the products, like if I have 99 organic milk products and only one that's non-organic, like, and I have to display top 6, I'd probably display most of them as organic because there's a data bias. So it's unclear if it's that or if it's a semantic search result issue, right? a good question though. Yeah, because I search for milk in this case, and it gives me all organic too. So might be there's a data bias or product bias, I would say.
But let's say if I search for no meat, right, it still give me a lot of
Yeah, then
steak,
they may be,
kitchen. But
yeah. What if you search for veggies? Does it give you meat?
that's probably
So maybe the fix here is go, of course, I understand what you're saying. But you see, this is the thing that we spoke about averaging embeddings, and you still think the content is about meat, even though you say it's no meat. So if your embedding is still saying, not able to understand that you have to negate meat,
yeah.
then there's a problem, right? But if you search for veggies, do you get veggies?
Yeah.
Okay, great. So, so there you go. That's probably what people will say. Like, no one searches for no meat, right? I understand people search for non-organic. I don't think people search for non-organic milk.
The semantic part.
I get what you're saying. I think maybe people search for no fat, low fat, organic milk, low fat or no fat. I think that's a good use case. But typically I would search for what I want. I want veggies or I want organic milk versus no organic milk. But I get what you're saying. I think the embeddings might be, there might be an issue there. It's also that, there may be layers before the embeddings get applied. Like we said, it's a multi-stage filtering. If those layers brought me all organic, what am I supposed to do? I'm going to do cosine similarity there. I'll get low scores. I'll rank them and I'll still display them anyway, even if, because that's kind of filtered down. So that could be another. It's something upstream that's bringing me these organic results. That could be one. It could be there's a data bias. That's the second. Third is the embeddings themselves are not very good at the negation of a product in representing a negation properly. So that could be very well be the case. Yeah. Good one. I think you guys should play around with it and figure out what's working, what's not working. But we'll look at some of the architecture as well, so we understand it better. Yeah, so data augmentation, since we are speaking about it, I just want to share that data augmentation is a very fairly common strategy that's used in for various reasons. Like, one is data augmentation because I need to train a smaller model, so I don't have enough data, I want to generate data. The other, for example, here is to actually train a smaller model completely from a larger model. So like, for example, Microsoft had come up with a Phi model sometime back. They now have Phi 2, Phi 3 and so on. It's a small language model, and it was trained with data from a high quality textbook data where the textbook itself got generated from a more powerful GPT. So it's saying, hey, the larger language model, it sees all kinds of data, Reddit data, it sees good data, not so good data and everything. But the small language model, better the quality of the data, the better its performance. So they actually tested asking the larger LLM, say, hey, can you just generate textbooks as training data for me? Because it's very structured and it has chapters and on these different topics. And then I'll use it to train my small language models, pre-training process. I'll just go through that using this. And it did better than just using other kinds of data that's available for small language models. So this is a different example of the use of data augmentation for pre-training. And then related to this is the use of LLM as annotators. And this is a very, very frequent use case is, sometimes you don't have, let's say, product information or category labels, or you don't have certain kinds of review sentiments or some identifiers that you want to use in your business, then use LLM as an annotator to annotate your data and then generate these tags, right? Also, you can use LLM as an annotator for your smaller language model and generate labels. And that's a very frequent use case. So you have this teacher-student relationship. A teacher is usually a large language model, and then student is a small language model. I mean, it doesn't even have to be very small. Like, you can use, let's say, Llama 3 70 billion to annotate data for Llama 3 1 billion or 8 billion. Or you can use the GPT 5.2 to annotate data for Llama 3 8 billion. And Llama 3 8 billion will meet your latency requirements for your business use case, but GPT 5.2 will not. So that's kind of an example where I'm still using the rich understanding of a large language model, but fine-tuning a smaller model for my specific business use case, right? So LLM can be used as annotators, paraphrasers, and LLM can also be used as a judge. So there's LLM as a judge to evaluate other LLMs, or I think in Google, for example, it's called auto-rater. So you auto-rate different aspects that you care about, like accuracy, tone, friendliness, or grammar, or whatever, of your model based on a different LLM, right? So you're kind of like putting human out of the loop. Just because you think the larger model is pretty accurate, but you can't use a larger model in deployment because of other reasons like latency and cost. Cost is another reason. There are studies that say that sometimes if you want to host open LLM models on GPUs yourself and then serve traffic, it can be like anywhere between 3 to 5 times or 3 to 10 times cheaper than actually using a GPT API or a proprietary Claude API or whatever, and then serving traffic based on that. So cost is another factor. Cost and latency are the reasons why we actually have this teacher-student relationship between large models and small models. So that's why we say, hey, all models are good. It just depends on your use case. Don't discard small models because the large models are powerful, because you may not be able to use large models for your business use case, right? So that's kind of getting into LLM design, but cool. So let's maybe sit in groups of 3, like you guys to do a breakout. Like we spend some time on understanding the Instacart use case. Would love for you guys to do the same with this use case where you have review, moderations, and insight. Like, imagine you're actually a team working on this, and you can use any company as a use case for that. And just maybe discuss A, B, C, D, E, F here. Take like 8 to 10 minutes and make it as real as possible, right? What are the issues that might come up? What are the signals that you'll use? Like, remember the signals that we use for Instacart. What are the kind of signals that you're going to use for this particular use case? And can you use just a large language model? Can you use a small language model? Do you need to use a sentence transformer? Which architecture are you going to pick? We just like sit in groups of 3 and you can brainstorm this for 8 to 10 minutes. Okay, so let's come back. Anything that came up for you as you were discussing? Yeah.
Are these categories exclusive? Like, can it be in multiple categories, or does it have to be in one of them?
Yeah, that's a good one. So a lot of times you come up with a starting point and you say, well, I think these things might overlap, or you can use one with the other. So that's where you go from just rigid classes to multi-label, for example. So if you want to treat it as a multi-class or multi-label, you can, one review can have, maybe it's highly passionate and also highly useful at the same time, right? So you have to really look at your categories and see if they're mutually exclusive or they overlap, right? Okay, that's a good observation. What else? Any other teams?
I was gonna say that it'd be a good idea to try to normalize out a reviewer's biases. So
more harsh than others.
Mm-hmm.
Or some reviewers might have like, I don't know, like a hidden intent of
Yeah.
weights for reviews. You can look at like,
Yeah, absolutely. I think that's important for both the customers as well as the company. If a few negative reviewers are highly bringing down the rating system, when you average the ratings out, then you can use this lens of filter to actually focus more on what's useful and give a rating based on that, right? Because like you might have sellers who are like, our ratings are always low because there's all these fringe people who kind of like bring the, I mean, they are sharing, all reviews are valid, but we want to say that there's so much more useful reviews that are not filtering into the rating system. So, these signals can help with rating as well, right? Because if you just go by rating, you might have a 5-star rating, right? If I just go by that, I might get a very different rating. So the way the rating is computed should also depend on some of these factors. Is like maybe there are outliers, I want to just exclude them and then compute the rating, right? So that's a good call out. Yeah, so let's say you could just use like a large language model and then label everything and get done, perfect. But then it might be too expensive to do that across all the reviews that you're getting for all the products. But you can still use it to do data annotation like we discussed earlier. Also, you might have a starting point. You might already have some labeled data, but it might not be sufficient for your model, right? So then you can do synthetic data generation like we spoke about earlier. You can replicate examples, like find paraphrase reviews and then use them as synthetic data. You can also annotate more data. That's another one. And for sure, even if you did training, you just say train a model and these labels make sense. When you actually, you have to have a benchmark on it. You have to benchmark and see if it's actually making sense or it's just you think it's making sense. And then you might actually change your labels or you might change your approach as well. So it can be very highly iterative in nature, right? What you begin with may not be where you end up. So believe it or not, this could very well be an interview question. When you interview for an ML role, it's like, hey, do this. You say, hey, just use LLM, you're done. It doesn't work that way, right? Because there's so many components of the design that you want to actually go into the details of it. So, and you have to ask, what is the end goal? What is the end goal of doing all of this? So the PM wants you to do it. Why do they want to do it? What do you think? Why is the PM interested in this?
sell more product.
Yeah, sell more product, and basically you have to look at your KPIs. Your KPIs are revenue. It could be your GMB, right? It could be the number of customers using the platform. So it could be seller satisfaction if you have sellers on board. So you have to look at all those metrics and see that this is actually the case. And at the end of the day, okay, you did your maybe offline benchmarking, but how do you know when you go to production, this is actually going to serve those KPIs? What do you do? What do you do to test that? Your KPIs are actually improving with this if you ship this product.
You look at the reviews, but you need to be able to evaluate them accurately.
Yeah, so what's the mechanism to do that?
A/B testing.
A/B testing, yeah. So you'll say, well, this is how I used to label reviews before or filter reviews before or display them before. Right now I have a new labeling system with this useful, not useful, and then I kind of percolate it into my front end. So my web page looks different. And now I see the customer satisfaction scores have gone up, or customers are saying that they found these reviews very engaging or useful or not. We see more faster conversions happening. So these are the things that we actually are able to test through an A/B test. You might not actually be able to directly see that when you build this model, but hopefully your hypothesis or your thinking is right that making these changes here will actually go all the way to KPI metrics through your A/B test. Right?
If you can identify highly useful and highly passionate ones, you can bubble them up, keep the balanced ones in the middle, and then push the obnoxious ones down.
Yeah,
But then if you present the
yeah,
customers that order,
yeah,
they will get this,
yeah,
if they are a balanced buyer themselves, they will read
Yeah.
and find the balanced ones.
yeah.
Or you can mix them up in a way.
That's a very good point. So if you go to, let's say, Amazon's page and you look at the reviews that they have, right at the top there is something that you might have noticed. What is that? Right above the reviews, there is a section that says customers say, and that's actually a summary of reviews, and the positives are listed first, and then it says some customers also say this might be a problem, but first the positives and the ones that are really useful are listed at the top, and then some things that are not working come up a little bit later. But there's no strong reactions in those reviews, right? It's catered towards what's useful and maybe a little bit of actual downsides that are valid downsides that are present. So these labels can also percolate into a AI review summary. You can summarize reviews using another AI model, and that can consume this that you just built as an input, because every review has a label, and multi-label maybe, not just a single label. You can have multi-labels, and then you can use that to then summarize and build summaries by labels or topics, and then you can also build an overall summary, and that's kind of what you see. Actually, if you go to Amazon, maybe you should just do that. Let's just do that to understand better. So we looked at an example of review moderation. So coming back to Instacart's model training architecture, they actually do two steps. There's a warm-up step for training, and then there is a you can say a refinement step. So even these things, right? Why do you warm up, and then why do you do this two-step training? There's a lot of creativity in these decisions, but sometimes it's also motivated by the ability to do better. For example, here they actually use a vanilla in-batch negative training samples, and here they use the adversarial training loss, right? So you can even say, like, first let me get a model, like we spoke before. First let's get a model, and it predicts positives and negatives, but the negatives, it might get low confidence in some cases. Let me increase the weight for those, and then I'll do it again. So that's kind of the intuition of boosting, as you improve on what you've already done and focus on the ones that you're not getting right. So that kind of justifies why you have this. But there may be other use cases where people don't do this, right? It's just very application dependent. So the interesting thing that they also do here is they tie the parameters between query and product in the first phase, so that the query and the product encoding can learn some shared attributes, shared representation. But then they untie it when they get to the second phase. But you start with the starting point that you had from the first phase, and then you build on it and say, now I specialize for query, I specialize for product. To begin with, I wanted something common, but now that I've learned that, let me specialize for query and product to get a separate embeddings there. And I also use a different loss function here, right?
So the query encoder parameters are also transferred to
Yes.
the query encoder in the second
As a starting point.
and also to the product encoder.
Correct.
Because they are the same.
They're the same. So starting point is the same.
Okay.
But then after you're done with the second phase, your embeddings and encodings will be different.
If there were a step 3, there would not be a transfer of parameters, right? It would be just a
Yeah,
repeat of
it'll be
step
different.
3.
Yeah, it'll be different. Yes. Yeah. But this is a interesting way that creative way that they decided to design and do it. So anyway, this is also a little bit instructive as you system design or ML design. You get these questions in interviews as well. There's always an offline component, training component, and there's the inference component. So at the top of this figure, you see the offline component is where you see the two-step process of training and want to get a product encoder and query encoder, right? And then you store the product embeddings. So the product embeddings, you don't have to compute live. You can store it ahead of time because the product isn't changing. The query embeddings, you can't predict what queries are coming. Sometimes you can cache queries, but if you're getting a new query, you cannot predict every single query. You can predict every single product embedding, but you cannot do the same for query. So that goes through, that's part of the inference process, right? The online process. So inference training. Okay. So the product embedding is computed ahead of time, and then you store it in a ANN, approximate nearest neighbor search index. So you can actually use an ANN service to do a fast search. Typically, people use things like phase or other algorithms that can do really fast search, semantic search, in an approximate manner. So you don't have to get the exact top 100 rankings. Even if you get approximate top 100, that's good enough, right? So that's what phase will guarantee, is it's going to be approximately right, but it's going to be fast. So when a query comes in at the inference time, first thing you do is generate the query embedding. Unless you're able to cache it, then you just use the embedding for the cached query, right? If it's not, then you have to actually, but this might include that. This might include caching. So the embedding generation might include caching. So you cache it, and then if it's a new one, then you have to go through the transformer. You have to go through all the layers of the transformer and then generate the embedding. And then once you have the query embedding Q, and then you have the product embedding P, now you do a dot product between query and all the possible product embeddings that you want to search across. And then you do a ranking and maybe filtering, and then you might have a separate ranking model as well. And then you can generate the top 20. Okay.
What does the DB database contain? Is it embeddings for the products?
Yeah, I think it's just if you have any new products that you've not computed already, you may want to store it in the.
That. I was hoping we could talk about actually, so maybe it. I'm gonna do that. Well, that's how we're gonna.
Sorry. Okay. One figure I want to show here is that they did a search for the query milk, and they wanted to look at products that are based on milk and then products that are based on milk chocolate. So this graph here, the orange and red, it looks at click-through rate. So for products that are plain milk, the click-through rate goes down like this through different products in that category. And for milk chocolate, it's kind of flat. The click-through rate is lower, which makes sense. But the gap kind of starts to reduce for certain products, right? But for embeddings, they show that if they look at milk, like the products that are mainly milk, for a milk query, the embedding score on the right here stays fairly high for products that are milk, right? But for products that are based on milk chocolate, there is a significant gap in the embedding score between the two. So this shows that embedding scores from the embeddings that they've computed through this training process are fairly robust to products that are of a different category than the query. But the click-through rate is not so robust. After a point, the click-through rate kind of like is similar. So so they say that as compared to click-through rate, embedding scores are much more robust in separating the two. This might still have issues with organic and non-organic milk, so that issue might still be there. But for fairly different products, the ones that are more similar and ones that are less similar, you see that there's a good separation between the embedding scores across the products. Cool. There's a couple of more things I want to mention. Yeah, since we have two presentations today, maybe we can go through that. So Instacart also looks at autocomplete, and so that's usually a prefix-based approach. Like you look at search queries and say, for a prefix P, what are the top, queries that come on Instacart? Okay, potatoes, parmesan cheese, pasta, etc. And you type in PE and say, okay, peanut butter, peppers, pepperoni, and so on. So this is based on whatever people have already searched, right? The prefix. So they say that now they see that sometimes a lot of the search results, or these are like autocomplete results, these are not actually the products, these are the autocomplete uh, queries that you can plug in. So you click on this, then the products come in. They can be very similar. Let me show an example here. Yeah. So if you type in a Mac, you see that if you didn't have a filter, then a lot of queries can be very similar. So mac cheese and macaroni cheese, they're the same. Mac cheese cups and macaroni cheese cups, they're the same, essentially the same. So it means you're giving less coverage for other kinds of search queries that can be completed from Mac, right? So they do a deduplication, just like the diversification example we looked at earlier. They use semantic search, embedding based cosine similarity, and see if it's very similar, then you filter it out, you deduplicate. So now instead of these two, you just have one of them. Instead of these two, you just have one of them, right? So this also increases, they saw that this actually increases the conversion for their customers by actually deduplicating.
So they can fit more useful suggestions.
Yes, and there is more coverage. Like for example, if for some reason I was looking for mac cheese frozen, I wouldn't have gotten it here because all these duplicates were taking up that space, right? So this is interesting thing where they actually diversify for deduplication. We looked at a diversity example earlier as well. So, and then you actually search. Let's say you want to search for pecans, then you get these search results. So they also have something for, the human brain is so good, right? You guys cannot read what this actually means, right? It's so weird, but you completely understand what it's saying. Handling misspellings. Our human brain can detect misspellings so easily. You can just look at a completely misspelled word and understand it. So how, they also have something where if you actually misspell the search query, like you're searching for grape, you type in GRAPW. If you didn't account for it, then you'd have no search results. But accounting for it, they're able to still surface relevant results based on a misspelled query. What do you think they are actually using to fix it from here to here? Is it semantic search?
Is it just similarity?
Is it similarity?
Because it can't be anything too complex because it has to run really quickly as you're typing.
Yeah. Like what if you had two products that are just differ by a letter, but they mean completely different, right? Then it wouldn't be similarity, right? So you'll have to, yeah, it's very interesting. I mean, you can use similarity search. I think you can definitely use it. But here they actually use edit distance. So you just replace a few characters or delete a few characters and see if you can generate something that's useful or close to what people have searched before. So for example, if you replace W by E, that's a replacement, that's an edit distance of 1. So they're actually doing character level modifications in the prefix to get to a prefix that's actually valid. And that's fast. That's something that you can do really fast, because you can just swap a few things and see, maybe I find something that's people have searched for in the history, and then I surface the results for that. So they didn't use AI here, it's just edit distance. Okay. Cool. So just thought we'll run through a business use case to see how what we have learned actually shows up in practice and the nuances of it, right? Because it's not just like, okay, I trained a model, okay, just use it. It's not like that. There's so many nuances that we have to look into: the data, the quality, the assessment, chaining of models. Sometimes it's not just one model, you have to use a bunch of models, like we saw with Instacart or with recommender systems. And you have to look at what signals you have from upstream, where is this going, how am I going to evaluate it online. So all of these make up the design of ML systems can get very complicated. Okay. So I don't think we have time for prompt engineering. We'll look at it in the next lecture. So I'll pause